Hi, I'm Ryan Kenke. You may have seen me in such fine quality chemistry educational videos as Lewis and Dots, what's up with that? And dots are electrons? Today we're going to be looking at Lewis dot diagrams and the bonding and how does that look. Okay, and in the back of me here I have the Lewis periodic table showing the outer shell, the valence electrons. Now, Lewis was a guy who long ago developed a system where students and professors and researchers can figure out, based off of the number of valence electrons for an atom, how is it that the atoms can connect to each other. Now, this bonding system isn't going to tell you if you have an ionic bond or a polar covalent bond or a nonpolar covalent bond. It's not going to tell you that, but it is going to be telling you about single bonds, double bonds, triple bonds. And we're going to get into that today. Okay, well, let's take a look here. If we look at the basic idea with the periodic chart, okay, all the chemistry happenings occur because of the valence electrons. So when we look at something like, for example, here in this particular group number 18, which is the last group here, you may notice that, well, they have got 8 dots around, like neon and argon, krypton, and xenon. They're completely full. Now, helium has got 2 and not 8, because remember, helium is small. It's very, very tiny, tiny atom. And it only needs 2 electrons to fill its outermost layer. And that's the key. We call those the noble gases or inert gases, okay, simply because they don't react. They don't need to react. They don't need to attract electrons, and they don't need to give away electrons. Now, can we push them to an extreme in order to get them to react? Yeah, but you have to push them to an extreme. You have to put a lot of energy into it. Now, what about these others? Well, there is something called, I call it the rule of Ocho. 8 is the magic number, where for the vast majority of these atoms, the amount of electrons, the number of electrons that they would need to be quote-unquote stable is 8. Yes, 8. 8 electrons, 8 valence electrons. Well, what about the electrons underneath the valence layer? Who cares? So let's look at it. Let's look at our group 1 here, our lovely little characters like hydrogen, lithium, sodium, potassium, rubidium, and cesium. They all have the same thing, 1 electron in there. Now, what's the magic number for them? 8. What's easier for them to do? Drop that 1 electron or go find 7 electrons to complete that outer shell. Well, this is also the same thing about if you're given an assignment. Are you going to take the easy way to get the A, or are you going to take the hard way to get the A? Yeah, people will take the easy way. It's human nature. These atoms, they're not stupid. They're going to do the exact same thing. So yeah, you've got that 1. Now, check this out. If you look at sodium here, for example, sodium has that 1 electron, and if it gives up that 1 electron, guess what? It's no longer a neutral charge. It is a +1 charge. It is a cation, okay, because of that. Now, we can look in group 2 here with calcium and magnesium. They got 2 electrons. It's a little bit harder to remove the electrons compared to the group 1, but if you take calcium and you take off those 2 electrons, now you have a +2 charge. Now, then here for 3 and 4, okay, it's kind of obvious as you're going through. Well, let's look at carbon here. Carbon can hook up with up to 4 other atoms at the same time, which is kind of interesting because carbon can be a +4 or it could be a -4 depending what it's connected with. Yeah, does make a bit of a difference, doesn't it? And then when we look at oxygen here, oxygen has 6. How many electrons would it want to get its magic 8? 2 electrons. 2, 2, 2 electrons as a result. And because of that, ladies and gentlemen, oxygen, it typically goes in with an oxidation number of -2 because it wants those 2 electrons to have its full outer shell. But in that process of in that full outer shell, guess what?
It has a -2 charge. Now that makes oxygen fairly destructive in terms of things like, respiration. We breathe in oxygen because it helps tear apart some things in the cell respiration, okay? And what do? We breathe out, we breathe in O2, we breathe out carbon dioxide. Now we look at fluorine and chlorine here in our halogen section, and we look at something like chlorine, for example. Chlorine has got its 7 electrons, so what's easier for chlorine to do? Drop the 7 or go pick up the 1? Right, you want to go pick up the 1 electron. Now with chlorine, what you guys see here for all these are at a charge of 0. They are neutral. If you drop electrons, you become the cation. If you pick up electrons, then you are an anion. You have that negative charge to it. So that's the basic idea behind this. Okay, how do we use Lewis dot diagrams to represent the connections that we have? Well, let's go ahead and let's take something fairly simple. Let's take good old hydrogen. So we can have hydrogen 2, and we can look up our chart. We say hydrogen, hey, hydrogen's got its 1 dot. Okay, so we know that hydrogen would look like this, which is also the same as saying it's a single bond. This is an example of a single bond. It's only 1 pair of electrons between 2 atoms. Okay, that would be kind of an important thing. Now, what about something like Cl2, where you have chlorine? Well, we're going to do it in 2 different colors so you can see. So we're going to look at Cl2. So we're going to have one of the Cl's, and it's going to have 1, 2, 3, 4, 5, 6, and 7. Now, I want to point something out to you about where you put those dots. Think of a box around the atom itself. You put 2 on each side, like you're seeing here. Okay? So we got the other chlorine. And I did the color so you guys can see why. You can see where the chlorines are sharing each other's electrons. But this, ladies and gentlemen, in the end, it's going to look, let me erase this. It's going to look like this. Okay? Now, do you have to show those other valence electrons out there? No, you don't have to. Really, the important thing to look at is that connection right here. That again, this is a single bond. But not all atoms are attaching by single bonds. Why don't we go ahead and let's try something else like carbon dioxide. Okay, so here's carbon dioxide. What do we know about it? Which one goes in the center of the molecule? Well, typically when you got something like this, okay, carbon tends to be the center of attraction, so to speak. So in this case here, we're going to look at carbon, and we are going to have 4 electrons attached to the carbon. Alrighty then, so we're going to have 1, 2, 3, 4. You'd say, wait a minute, why in the world did you put that? Well, watch what happens when we put in the oxygen. Okay, I'm going to put an oxygen atom here, and I'm going to put 1, 2, 3, 4, 5, 6. So there's our 6. Here's our red oxygen with its 6 electrons there. Here's our carbon with our 4 electrons. Now I'm going to draw another oxygen here, and I'm going to draw its 6 electrons like this. This is what we have. Okay, so we have carbon dioxide. This is a double bond. Now, why would they need to have a double bond for this? Well, remember, the main objective for each of these atoms is to achieve their ocho. Right, the ocho. The 8 valence electrons. Very important. Can't emphasize that enough. So let's look at this. If I go and I cover up all this, well, let me try that. If I cover this up, how many electrons does this red oxygen have? Well, it's got its 6 red, and it's the 2 electrons it happens to share with carbon. So oxygen's got its 8. It's good. You'd say, but wait a minute, oxygen is sharing some of those electrons with the carbon. Right, it does. Okay, that's okay. Now if I cover up this oxygen and this oxygen here, how many electrons do we have around the carbon? 1, 2, 3, 4, 5, 6, 7, 8. 8 electrons. Is carbon good to go? You betcha it is. Now, hold on. Let's be honest. Let's try the last one. Let's cover these up. Look at the green oxygen. How many electrons does it have? 1, 2, 3, 4, 5, 6, 7, 8. The whole thing is balanced. Woo! Yeah. So what would that look like in terms of dots like this? Well, carbon would look like this. You would use 2 bars to represent the double bond, compared to the single bar with the single bond. Okay? So we did 3 examples so far. Why don't we go ahead and let's try for another one. Let's go ahead and let's try nitrogen. Now nitrogen, an N2, nitrogen, I look up, I see, okay, there's 5 electrons. Okay, so let's go with nitrogen. Nitrogen has 5 electrons. So I'm going to put one here. I'm going to put one nitrogen here, and I'm going to put another nitrogen here. Okay, so we have blue and green, so we can tell who's who. Now the thing is, with nitrogen, the main objective is to get 8 electrons. That one nitrogen gets 8 electrons. Now this nitrogen will already have 1, 2, whoops. Let me erase here. So we're going to have 1, 2, 3, 4. We're going to put the 5th one here. We're just going to try that for a moment. Now we're going to go ahead, we're going to have the other nitrogen with its 5 electrons. So, each nitrogen has its 5 valence electrons, and now the question comes down to is, you've got 3 pairs of electrons being shared. That's a triple bond. But, wait a minute, what else do we have here? Let's check it, let's make sure we're good. We cover up this nitrogen and we see how many electron dots we have. 2, 4, 6, 8. We cover up this one over here and we have 2, 4, 6, 8. Good to go. Both nitrogens have their 8 valence electrons. 8 is that magic number. Booyah. It's good to go. What would that look like? Well, the nitrogen would look like this. Okay? That would be tough. All right. So I've explained to you the idea about the electron dots, that they are valence electrons. Okay? That they are electron dots. They represent valence electrons. Okay? The magic number for the vast majority is going to be 8. Okay? These guys on this end with 1 or 2 electrons, they are more likely to get rid of them than go pick up enough to make 8. Whereas if you go on this side here, they want to go and pick up electrons. This would explain things like sodium and chlorine coming together. Now it is a metal with a non-metal. And if you noticed here, so far, I have connected non-metals to each other. There is a limit because when you look at something like sodium that's got 1 electron, remember, okay, we can look at NaCl, for example, and here's sodium with its 1 electron, and here's chlorine with its 7 electrons. So that at the end, it's going to look like NaCl. Now, I want to point something out. If you block out the Na, Cl has got its 8 electrons. If you block out the Cl, you say, wait a minute, but Na doesn't have its 8 electrons. Well, remember, it's a metal. And because of that, it's an alkali, earth metal, to be specific. Okay, but remember, when the sodium gives up that one electron that transfers over to the chlorine, there is the 8 electrons underneath that layer that allows sodium to be okay. So when you have something like sodium, for example, here, with its 1 electron, it has a charge of 0. That's what it is. When chlorine has its original charge is also 0, because that's the normal number of electrons that they have. Now, neither of them are okay with this. So sodium gets rid of its electron. Okay? So sodium gets rid of its electron, it now becomes a positive charge. It is now what we call a cation. Okay? On the other side of the coin, if we look at chlorine, let me write that up in green. If we look at chlorine on the other hand, okay, when chlorine picks up an electron, okay, where now chlorine is now going to have its, and we'll put in the red dot to represent it picked it up from sodium. Now the charge on chlorine is no longer a 0, it is now a -1 because it picked up that 1 electron. Remember, 1 electron minus 1 charge. And that's what you're seeing here. So what happens? Well, what you end up getting is sodium with a +1 charge, chlorine with a -1 charge. Now, as I taught my chemistry guys, what does Paula Abdul say? Opposites attract. And what you're going to get as bonding goes, sodium transfers its electron over from sodium to chlorine, and then they end up joining together to form a single bond, NaCl, but this is an ionic bond. Okay? And that would be the subject for another video. Hey, I hope this helped you guys out a little bit with electron dot diagrams. I can go with one more, where we can go and look at something like CH4 very quickly. So what's up with the carbon? Well, carbon has got its 4 electrons, and hydrogen has 1 electron, and that's the connection. How would you write that up? C, H, 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 like that. That's what it would look like. Now, do Lewis dot structures can they tell us about the shape of the molecules? Not really. What the Lewis dot structures tell you is how is it the atoms are connecting to each other? How many electrons do they share between? It doesn't tell you what kind of a bond, polar, nonpolar, covalent, okay, ionic. It doesn't tell you that, but it doesn't tell you the shape of the molecule either. That would be the subject for other videos to come down the road. Hey, I hope this helps you guys out. Until then, I am Ryan Conkey. Take care.